And that takes us to the next talk by Professor Ghim Wei Ho. She's from NUS Singapore and also belongs to the Institute of Materials Research and Engineering, A-Star Singapore. And she's going to talk on nanocomposite for photothermal-driven catalysis and energy generation.
Thanks for the kind introduction. And my name is Ghim Wei from National University of Singapore. And first off, I want to thank the IWAM board members, especially Tony, for giving me this opportunity to speak at this conference. This morning, I'm going to focus on nanocomposites for photothermal-driven catalysis and energy generation. So we all know that the sun sends a tremendous amount of energy every day. However, the challenge has always been in capturing and using this energy effectively. Why? Well, despite the abundance of solar energy, the ability to harness, especially the low-grade solar heat, is limited with existing technologies because of very small temperature difference and temporal heat variability or fluctuation. So intensive efforts have been devoted to design photothermal material to better utilize the low-grade heat. So what makes this material so special, and what are its requisites? So first off, the material should have a high solar absorbance or broadband absorption, and it should have a low optical reflectance or transmittance near zero, where heat is preferably absorbed or retained rather than reflected or released. And it should have a low conduction, convection, and radiation heat losses through very effective thermal management. And lastly, it should allow efficient light-to-heat conversion, where light is mostly converted into heat instead of other forms of energy or being re-radiated. So essentially, what we are looking at is the future of a solar energy utilization. So by focusing on the designing of an innovative photothermal composite, we are hoping to take a significant stride forward in making the solar energy more accessible and also more efficient for various applications. So here I would like to say that the most common use of photothermal material is for solar heat conversion for water vaporization. So while we have achieved a high level of efficiency in using photothermal energy for water vaporization, we must acknowledge that there are still plenty of underexplored energy sources that are waiting to be developed. So here I've highlighted that there are sort of many opportunities that are overlooked in trying to get more energy transfer processes and potential energy sources that one can tap from the solar-driven interfacial evaporation system, as shown here. So just for illustration, hot vapor, we all know that it has high thermal energy, also has high kinetic energy. And it can be directly used as a heat source or convert into other forms of energy to drive a device mechanically or reaction chemically. Another illustration would be benefiting from the photothermal heat localization effect. The top surfaces of a photothermal material are of higher temperature than the surrounding as well as the underlying matrix. And these temperature differences promise useful thermal energy that can be extracted for energy generation and perhaps also to enhance the mass transport dynamics of ion diffusions or carrier transportation. So there are a lot of other potential energy sources that one can consider from all the lists here: temperature fluctuation, high pressure, change in salinity, humidity, and so on and so forth. So by carefully designing the materials and also device, one can exploit multiple sources of such energy synergistically to realize a diverse application. So please note that the application that I've outlined here are by no means comprehensive, but they serve to outline, or rather to illustrate the potential breadth that photothermal materials utility in the ongoing research evolution. So here I'd like to show you a summary of the various energy harvesting mechanisms that can be coupled to a photothermal evaporation system, and they include thermoelectric, Seebeck effect, thermogalvanic, pyropiezoelectric, tribal electrostatic, ionovoltaic, as well as photovoltaic. And among them, the thermoelectric and the photovoltaic mechanisms stand out because they are typically associated with higher power densities, usually exceeding 1 watt per meter square. And this is due in part to the fact that their energy profiles are well matched to the commercial applications, leading to a highly efficient as well as reliable energy harvester. So other sort of mentioned energy harvesters mostly operate in a lower energy power densities, which is less than 1 microwatt per meter square. However, the research landscape is evolving, and recent research have already successfully demonstrated that it's possible for different photothermal systems to be synergistically coupled for multiple applications with much higher efficiency. So this coupling can be achieved with minimal or no trade-offs. So what does it mean for this field? So we can now start to get a much higher or harness a much higher energy that is enhanced by photothermal effect, especially for the low-grade waste heat. And importantly, this can be achieved with significantly improved systems' overall efficiency. So for a more holistic picture, here shows a photothermal research paradigm, and as you can see, there are various aspects of consideration that you need to take in when you want to design a photothermal system. So it can be making the right choice of solar absorbent material, whether it's plasmonic metals, semiconductor, or carbon-based materials, to fulfilling some of its important prerequisites such as broadband absorption, thermal management, and optical management. And once the materials are dialed in, our focus will shift to the system design, whether it's for volumetric bulk system design or surface interface kind of design, or perhaps isolated or embedded design. So then we reach the culmination of our research efforts, that is trying to construct a device that are very specific for certain applications. And this is where the theory meets the practice, whether we are aiming for energy generation, catalysis, water production, or even applications that we have yet to envision. So to underscore the importance of this field, I would like to emphasize that photothermal conversion is indeed a promising avenue towards clean and sustainable energy, water, and environmental solutions. So in essence, in photothermal research is a tapestry of interdisciplinary efforts where material science, design ingenuity, and application-specific engineering come together. So a brief introduction of my research group, focus and passion. So we are deeply interested in solar-enabled technologies, particularly photon and thermal energy conversion. And our research basically spans across a few exciting areas: solar chemical, solar water, and solar electronics. And these three thematic solar trusts aims to harvest the next generation nanostructured material, unique physical and chemical properties that will impact the sustainable catalysis, energy, water, and electronics field. So in today's talk, I will be covering through some of the works that we have done, mostly in materials, optical, and thermal tuning for hybrid catalysis and desalination application. It's more from the engineering field since I'm coming from engineering department. So as we continue our journey in the photothermal research, I'm reminded of our beginnings, and that is back in 2015 when we started then trying to harness the light to heat conversion, aiming mostly for photocatalysis, yet serendipitously we realized that we could also at the same time enhance the water evaporation. And this discovery led us down to the path of dual functionality. So we see the potential of marrying catalysis and desalination through the photothermal processes. And this is a turning point for us that we could be realizing that we could actually solve or tackle two sort of critical problems simultaneously. So for the design strategies, we have used plasmonic nanoparticles, in this case silver, because it has proven to have a stable photocatalysis under continuous seawater and light irradiation. And then we engineered a core shell structures with the plasmonic as a core, and then the silica as a heat insulation. And that's mainly for thermal management. So if you have captured enough sun and to convert into heat, the next thing you should do is try to keep the thermal all within the catalyst material. And then lastly, we demonstrate that this is a viable material for catalysis and desalination. So here shows the hydrogen plot and of different temperature with 4 different sacrificial agents. It's quite apparent that the temperature elevation increases the efficiency of hydrogen production. And among them, the glycerol shows the highest improvement, about 57%, when temperature increases from 30 to 90 degrees Celsius. And he has postulated that it's due to the increased whole scavenging activities of the sacrificial agent. And this is in turn correlates with the improved or prolonged lifetime of the photo-generated carriers. Then the photothermal enhanced catalytic hydrogen generation can be observed for both water as well as seawater. And in the hydrogen generation for seawater are consistently lower than that of water. And the reason for that is because of the formation of chlorine radicals due to whole oxidation, which then the chlorine would then reduce by the photogenerated electrons, and this creates an electron pathway that competes with photocatalytic hydrogen reaction. Notably, the chlorine ions concentration remains unchanged with time, and this is very significant because basically it elevates the concern of producing a toxic gas or acid in our system. Then we show that the semiconductor catalyst has a stable reactivity, and this is very important because stability is the cornerstone of any application, which to ensure the consistency of the performance with time. Then we went on to design a passive prototype reactor, which has a parabolic trough that focuses the sunlight to the bottom part of the quartz tube, whereas the rest of the quartz tube are insulated to prevent excessive heat loss. And we have a hydrogen outlet with filter that separates the water vapor from the hydrogen. The steam has not gone to waste. It's condensed into water at the condenser unit. And here shows the outdoor real sunlight conditions performance. And the time-dependent study of the solar intensity and reaction temperature shows that despite the fluctuation of solar intensity, we could obtain a fairly stable and high hydrogen production. And of course, at the same time, steam can be produced about 6 liters per meter square per hour. And again, here the chlorine ions, absence of chlorine ions in the condensate indicates the production of fresh water. So as we advance to the next phase of photothermal research, we reflected on the previous sort of achievement and also lessons learned. So while we have achieved or successfully demonstrated simultaneous harvesting of solar water and hydrogen, we noted that a high evaporation rate does not necessarily translate to efficient water harvesting, because evaporation is calculated based on water mass loss into open ambient instead of having an efficient water collection system. So based on these findings, our subsequent work took a slightly different approach. So similarly, we have used photothermal for catalysis and desalination, but this time we have designed a photothermal membrane distillation in order to enable a higher water to distillate conversion. And we have also used silver plasmonic nanoparticles, but instead of suspension base, we have constructed a 3D photothermal catalytic membrane which have proven to have much higher performance. So allow me to quickly introduce the PMD system. So essentially, it's a conventional membrane distillation that is hybrid with light to heat conversion input. And the idea is to reduce the energy for heating the feed and to enhance the driving force for vapor permeation. So here shows the graphical imaged or representation of the processes and the different sort of consideration that you need to take into account when designing this system. So here you can see that you need to take care of the materials properties, materials that incorporated light harvesting, thermal management, as well as the condenser design itself. So as you can see from here, that it's all about holistic integration of the system before you have a very efficient output. So our idea is actually to incorporate a solar absorber and catalytic active layer at the membrane system. And that is the heart of our system, basically trying to provide the localized heating to enhance the catalysis as well as desalination at the same time. So with the PMD design in mind, we have prepared a 3D hybrid organic-inorganic photothermal gel with aligned pores, and this can be done by incorporating TiO2 silver nanofibers into a chitosan matrix, and that's done by a directional freezing method. And the TiO2 nanofibers are cross-linked and very well dispersed in the chitosan matrix, which shown to have aligned pores as well as collimer walls. And the chitosan is not chosen at random. It actually has a sort of superior water-absorbing properties to allow the replenishment of the water, which is needed for the photothermal vaporization and catalysis. So in our quest to maximize the efficiency of the solar energy conversion, we have employed the optical spectral management strategy and to promote the designated solar to chemical or solar to thermal conversion. So what I mean by that is that the high energy UV photons are designated for photothermal catalytic redox reaction, and the lower energy visible photon is designated for plasmonic heating, while the lowest energy infrared is absorbed by the gel for photoheating as well. So with that, upon addition of visible and IR illumination, we can see that the hydrogen performance have improved by 400%. And in order to validate the role of the plasmonic nanoparticles in this enhancement, we have used various monochromatic light sources with different wavelengths to study the hydrogen production. And you can see that the plasmonic localized heating of the hydrogen production matches very well with the silver resonance band at 450 to 505 nanometer. So basically, this confirms that it's the plasmonic photothermal effect that have indeed enhanced the catalytic reaction. And then dual condensate hydrogen cell has been set up, as shown here, and hydrogen production can be produced from both water and seawater, and the condensate can be collected as well. So here you see that the salt rejection ability of various ions can reach up to 99.9% for this system. And the enhancement condensate collection is associated to the confined photothermal heating at the feed membrane interface. And this can be reflected in the temperature difference between the two with and without the photothermal membrane, about 15 degrees Celsius. And this temperature difference then creates a favorable vapor pressure gradient that improves the performance. So moreover, these structures has a macro structures that are aligned, and this allows a pathway to facilitate the transport of the liquid as well as gaseous product. At the same time, it improves the heat conduction along the microchannels. So based on the promising sort of results from the single cell, we have scaled out the prototype to 3x3 cell and shown a larger outdoor prototype for proof of concept demonstration to collect both the fresh water as well as hydrogen from the seawater. And the PMD design has indeed shown a much better performance compared to the suspension-based kind of system. So to sort of push the boundaries of the photothermal research, we went on to focus mainly on membrane-based matrix. And the preference for this kind of membrane-based matrix catalyst is rooted in the inherent properties that the membrane technologies bring. For instance, ease of operation, compact footprint, scalability, and high industrial readiness. So all these qualities made the membrane a much more attractive choice for a wide range of applications. So in our latest work, we have delved into an exciting area that is on energy-coupled functions that is driven by chemical, electromagnetic, thermal, and electrical sort of interactions with this membrane. And we have also explored the coupled to catalyze traits, which is a feature that, or characteristics that could potentially fulfill all chemists' dream, that is to develop an engineered membrane to mediate a targeted or specific chemical transformation much more efficiently. So in this work, I would like to show you that in a typical aqueous system, due to the lowest free energy barrier, the nuclei formation is usually preferred at a liquid-solid interface over the homogeneous nucleation or over the liquid-air interface. So in this work, we have used a partially hydrolyzed polyvinyl acetate hydrogel, and its molecular structure is shown in the FTR here. And we have the acetal group, which makes it hydrophobic, and then hydroxyl group, which makes it hydrophilic. And this gives it ability to have insolubility as well as water swelling ability in the aqueous solution, respectively. And here shows the microstructure diagrams as well as atomic pair distribution function, and the observed decrease in the O distance of the hydrogel coating under compressive state is because of the decrease in the density of hydrogen bonds between the PVA system and the water network. And then this confirms an enhancement in the structural order degree of the PVAC network and water molecules, then forming a water-permeated hydrogel, which repels any sort of approaching particles from a bulk solution. So with this, we have realized a novel solid-liquid interface shielding strategy, which shifts the nucleation preference now to the air-liquid interface, so allowing us to harvest or to create membrane right on the liquid surface. So here I'd like to show you the pilot testing of the silver reaction on the proposed SLS mechanism on the PVAC coated vessel. As you can see, a piece of freestanding silver as well as continuous membrane can be obtained right on the liquid surface. And this conductivity measurement shows its structural homogeneity in terms of morphology, density, and thickness in a macro scale, and in a nanoscale or microscale, homogeneity can be confirmed using the scanning electron microscope. And the freestanding silver membrane has a thickness about 189 nanometer, and this thickness can be tuned depending on reaction parameters. And it has a comparable Young modulus about 96.3 gigapascal as compared to a bulk polycrystalline counterpart. And the other thing is that it has excellent flexibility, as seen from here, the absence of fracture in the artificially created wrinkles of a bending radius about several micrometers. So we went on to validate that the SLS technique is universal for direct synthesis of various inorganic membranes. And as you can see here, the present membrane library consists of 42 elements and 5 representative membranes in 8 of these categories of classic materials, from elemental substance, oxide, sulfides, halides, oxide, metallics, non-metallics, as well as coordination polymers. So all these are based on 3 very common aqueous reactions, that is redox reaction, hydrolysis, as well as precipitation reaction. So we can routinely now prepare a freestanding inorganic membrane of several cm in dimension, and it's determined by the vessel size. Okay, let me quickly go through the formation mechanism of the membrane. So by exploiting the size-dependent absorption and reflection of silver, we have developed a fast spectroscopic method to identify all the critical states in this formation of the membrane. So essentially, the successful membrane formation depends on 2 stages, that is Brownian as well as Churros effect. So we start off with the Brownian motion, which is a random motion and collision between suspended particles. And this basically dominates the initial aggregation as well as transformation into a 2D clusters. And followed by that, we have the capillary attraction, also known as the churros effect, that would drive the self-assembly of these isolated Brownian 2D clusters to mutually attract and then form a quasi-bicontinuous network. And thereafter, the emitter-shaped vacant region are progressively filled up by the particles and evolving into a well-defined closed through-hole pores. And if this process is allowed to continue, the holy membrane will eventually become a compact membrane. So the quasi-bicontinuous network is shown to be isotropic and also fractal in nature, which is evident from the TM images here. And these basically prove that it's confirmed it's derived from a combined Brownian and churros effect rather than from a single dynamic mechanism. So other than a simplex membrane, we also tried to prepare a multiplex membrane, which is derived from a monocomposition of a silver membrane. And this includes silver sulfide silver, cerium oxide silver, as well as iron oxide hydroxide silver. And this one is essentially one membrane grown on top of the other membrane, which is seamlessly sort of integrated with bifacial features that combines best of both materials together in a singular structure. So here are all the materials characterization to prove the materials composition as well as structural design of the complex or multiplex membrane. So the fact that we could, the ability to extend this kind of topological complexity from simplex to multiplex membrane means that we could now start to prepare a user-defined or user-prescribed kind of membrane-based catalyst for any sort of specific reactions. They are catered for large-scale industry applications. So we feel that the potential here is vast because it offers a new level of customization and manufacturing efficacy for membrane industries. So also excitingly, we have availability of extensive membrane library and a variety of energy that can be coupled to this membrane from chemical, mechanical, light, thermal, electrical, as well as magnetic field. So we are focused mainly on the solar photon energy because of the fact that it's a sustainable solution for catalysis and desalination. And in order to achieve it, we have prepared an ultra-thin stack silver or TiO2 or semiconductor metal membrane and performed a photon spatial disproportionation, which shows that it has separated electrons and holes, and it also has augmented oxidation and reduction, which can be used for catalysis and desalination, or mainly for catalysis, actually. So through fine-tuning of the through-hole pore size, as well as particle size, chemical composition, as well as topological structure, we can tune the membrane whatever we like or whatever composition that we like. And basically offers an unparalleled level of control over functionality. So it's a testament of the flexibility and adaptability of our approach in meeting the diverse needs of industry application with precision and as well as with efficiency. Okay, to further expand or rather to broaden the horizon of our photothermal research, we have also explored photothermal for pyroelectricity. So here we have used a nanophotonic structures of periodic composite for a thermal reflectance purpose, and we have a multi-layer of silica, insulative silica for thermal management. And here we have shown the film to be very effective for cooling purpose, purification, as well as pyroelectricity. So here we have TiO2 silica. So instead of core shell structure, now we have periodically stacked them, as you can see in the layer architecture in the SEM picture here. And they are mesoporous in nature in the TM images and SEM images here. So they are layered structures with high refractive index, alternate with a low refractive index, and they are coupled with ferroelectric material to enable a multifunction VOC degradation, solar heat reflection, as well as energy generation. So here shows the actual prototypes material or product, and it has a high optical transparency. It's anti-glare as well as anti-scratch, which means that it's well suited for smart window and also smart display applications. So here shows all the work that we have undertaken to assess or to evaluate the cooling performance. And the matrix for cooling assessment includes indoor solar transmittance as well as the resultant temperature reduction. And with the film parameter optimization, we could suppress the near and out solar heat down to 14% and maintain a high optical visible light transmission about 80%. And we have achieved a delicate balance between keeping out the solar heat and letting in plenty of light into the room to ensure there is a good indoor lighting. So with a selective UV visible and near and out spectral transmission, tuning, and optimization, we have a direct and tangible impact on the indoor space with a temperature reduction about 4.1 degrees Celsius black body and 1.3 degrees Celsius air. And here, IR tomography images shows that the film, the nanophotonic film, has a very consistent cooling results. And TiO2 being one of the key composition of the film means that it can allow or it can enable a photocatalytic degradation of organic air pollutants to be realized. Then here, because of we all know that the temporal temperature fluctuation exists everywhere at ambient because of wind, cloud cover, because of sun, and because of various heating and cooling sources that's around us. We can try to harvest this kind of temperature fluctuation into a viable heat to electricity conversion. So in order to do this, we have incorporated a ferroelectric film into the back-reflected solar reflective heating nanophotonic film, and the integrated film shows a much better performance in terms of open circuit voltage as well as short circuit current, about 150% at the 9 millihertz, which is attributed to increased temperature harnessing as well as rate of temperature change. So in other words, the back-reflected heat, instead of dumping into the environment and causing the detrimental urban heat island effect, we are trying to harvest this energy to enhance the pyroelectricity for the electricity generation, and that's happening under one sun condition. So we went on to build a large-scale solar reflective cooling and energy generation prototype to conduct some feasibility testing. And our preliminary result shows promising as well as encouraging results in terms of indoor cooling performance of up to 4 degrees Celsius. However, the pyroelectricity energy harvesting has to be enhanced. So in order to enhance the pyroelectricity, we have recently exploited the localized photothermal effect to induce polarization ripples, and that is arising from the in-plane temperature fluctuation of the transverse pyroelectricity. And we all know that a conventional pyro device has a heat flux propagation and dissipation in the out-of-plane direction, meaning in Z direction along the thickness, device thickness. And in our design, we have transverse pyro generator, TPG, and it has a photothermal hotspot that allows the heat propagation and polarization along the in-plane direction, meaning in the XY direction in a transverse sort of direction. So by doing that, we have a localized intense rate of heat variation that allows us to have a larger polarization ripples or a larger sort of dipole shifts that is attributed to a higher electrostatic induced surface charge density. And it comes from the fact that we have augmented the non-uniform transverse polarization, and also we have prolonged the heat propagation duration. So consequently, we have the TPG output that outperforms the conventional devices in terms of the same magnification and intensity, as you can see from this plot here. So here, the temperature profiles of a TPG has shown a 200% increment in the temperature harvesting, as well as up to 29 folds in terms of heat variation harvesting. That's nearly 2 orders of magnitude, or about 2 orders of magnitude. And in regards to the spatial temporal temperature distribution, we can see that the TPG during heating and the cooling cycles has a multiple temperature contours, which affirms that it has a delineated thermal ripple fluctuation. And this is originating from the photothermal hotspot in the center, and it propagates outward to the adjacent or peripheral area. And also pyroelectric coefficient has been used to quantify the polarization in the in-plane heat direction. So here it shows that current and as well as voltage has been increased using the TPG design. And the TPG output can also be quantified using the voltage charge integration, where area under the curve defines the energy harvested by the TPG that far exceeds that of the conventional device. So in order to demonstrate the scalability, as well as stability and practicality of the low-grade solar heat harvesting, we have designed a modular system of a TPG system, as well as a conventional system of 3x3 units. And the enhanced output of the TPG shows about 536% in terms of in the series configuration, and 379% improvement in the parallel configuration. And besides that, the steady charge output in the 1,000 heating and cooling cycles show that there is negligible current leakages, as well as electrostatics that are independent of the cycling. So here, I want to quickly show you the state-of-art peak power density comparison. It shows that our TPG has a high solar heat harvesting up to 38 milliwatts per meter square under 1 sun. So the implication is that at very low solar intensity of less than 0.1 kilowatt per meter square, which is an everyday form of illumination for countries that are outside equator or places that are shielded or in shading or are sort of blocked by the sunlight, they can now find a useful sort of purpose. So in the interest of time, let me just go through quickly. This is another work that I've done, photothermal actuation and energy harvesting. So this can also be extended for soft robotic system, which we have shown in our work, and I won't discuss here. And lastly, I just want to say that photothermal can also be exploited for environmental remediation. This is our most recent work, and what we have shown is that we have electrostatic photothermal membrane that has this photothermal heating 80 degrees Celsius within 20 seconds under 1 sun, and it can be used for microalgae extraction and harvesting, which has proven to be an effective strategy for proactive water bloom prevention. So the electrostatic basically provides a selective absorption, and then it performs the deactivation of the toxic intracellular substance, which allows it to turn into a valuable biomass. So by having this valuable biomass, we can now also think about how to make it useful for future sustainable energy as well as food sources. But in any case, the water bloom is a threat to aquatic environment and also water resources. It can be solved using this electrostatic photothermal membrane. So this is our recent work. So with that, I stop, and I just want to acknowledge my students and also the funding agency, A-STAR, MOE, as well as NRF. And thank you very much for your attention.
Thank you so much. Actually, I have a question regarding the electronic interaction between, for example, when you talk about the photothermal desalination, right? So I'm just wondering, do you think there is any kind of electronic interaction between silver nanoparticles and titanium dioxide? Especially, I know that you use the heat to do the reaction, but plasmonic material also, they got the heat from the charge recombination, right? So, and also, I'm pretty sure there is electron injection from silver nanoparticles to titanium dioxide. So my question now, do you think this playing any role in your process? And what I can comment also that if you use a wide band gap semiconductor, I believe you might get even better efficiency. And my second point about the stability, because sometimes this kind of plasmonic nanomaterial, they are not quite stable for long term, so you might get really a drop in the efficiency due to the low stability. Thank you so much.
Yeah, thank you very much for your question. You're spot on in the sense that there's always stability issues. So we always try to use wide bandgap semiconductor. So I have, I didn't show the work here, but today I just focus mainly on TiO2 and silver, because so far the testing for silver and TiO2 has proven to be very stable. The silver, like what you say, it does absorb the light. At the same time, it also does the co-catalyst reaction. So basically, it can harness the separate electron hole pairs generation. So we studied that, and we have also tried different sort of materials. And there are materials that clashes, meaning that the charge recombination will be affected if, you can't have the best of both sometimes. So we realized that if you want to have photoheating and at the same time charge separation, these two materials has to be decoupled. So only the recent work that we have shown in, which we have published, which we show that it's possible to have two types of material inside. One does the charge separation, and the other does the photothermal heating. And then with that, we have increased the mass reaction. Yeah, but we can talk about it more.
Yeah, any other quick question? Yes, Judith, the last question.
Really beautiful talk, Ghim Wei. Thank you.
Thank you.
How does your photothermal desalination compete with green energy on the grids and, creating desalination like we have just down the road here, a big desalination plant with? How much better do you have to do? That's what I just haven't got that picture.
A lot more. The truth is that we are trying to go into a sustainable way, but obviously we are not there yet because the efficiency needs to be a lot more higher. So that's why we are trying to go in the direction of membrane system, and hopefully we can incorporate that into the system. But the other thing we have to worry is about the light. How do you introduce the light into the system? Yeah.
The other quick question is, you were comparing your PVDF data with barium titanate, which of course has a much lower pyroelectric coefficient. So is that really a valid comparison?
For PVDF,
Yeah.
you mean? Not entirely. I agree. Yes.
It's another ferroelectric, but
yes.
PVDF, of course, is a soft material which deforms a lot.
So we use PVDF a lot. In fact, the actuator that I did not manage to present, that was used because we're trying to do a flexible soft robotic system. And then we also use PVDF for the film coating, for the solar reflective coating and cooling. It's because it's easy to process using deep coating method. So what we did is very simply deep coat into the glass, multiple layers. If you see that nanophotonic structures, you allow us to process it very easily. Yeah. So there are sort of, I understand what you mean. There's a compromise between.
It is amazing ferroelectric, actually, isn't it? It's being used everywhere now in all sorts.
Yes. But we're still trying to tune, adding copolymers and stuff like that to make it much better in terms of the performance.
And it's also been used in batteries for charge separation.
Yes, that's right. Yeah.
Maybe we can take over the discussion for the tea. Let's thank Professor Ghim Wei Ho for a wonderful talk.